So the C&D recycling process, that process map that we have just seen is mostly same for globally. The only two differences that we can see in different recycling plants are with respect to the number of stages of the crushing that is done, and the other thing is type of the crushes that they usually use. So normally what happen, depending upon the size and the requirement, so we can have a single crushing stage wherein one crusher will be kept and the aggregates will be the concrete chunks will be crushed. Uh, Also we can have two crushers. So one crusher, let's say, for reducing the size from 500 mm to 150 mm, and the other crusher to reduce the size from 150 mm to coarse aggregate and fine aggregate, right? And nowadays tertiary stage crushing is also been seen. So so what happens in the tertiary stage crushing cycles, advanced crushers are kept. For example, there are vertical shaft impact crusher and horizontal shaft impact crusher. These are considered to be advanced crusher which can improve the shape properties of the aggregates. So these crushers are kept at the end to improve the morphological properties of the aggregates, especially the fine aggregates. Uh, the other difference that we can see in different recycling plants is the type of the crusher. So normally we have jaw crusher wherein the aggregates are broken by providing the compression. So normally jaw crushers are used to break the strong aggregates, right? So in most of the plant, if you see, the first crusher will always be jaw crusher. Then we have vertical shaft impact crusher, horizontal shaft impact crusher, which applies impact energy to break the aggregates. And then apart from that, we can have gyratory crushers, we can have cone crushers also as a second crusher or the third crusher in different crushing stages. So these are some of the photos which shows how the recycling is done. So this is a recycling plant in Chennai. If you see, the C&D waste material is coming here, and then initial segregation is happening, and after that it is fed into the system. So, and this is the magnetic separator which is removing the loosened steel bars, and thereafter it is the C&D waste is transferred from this feeding unit to the crushing unit. So this is a crusher, and then in between people will be standing for initial segregation. And after this C&D waste is crushed to small sizes, for example here, at least in this particular case, the input size of the input is around 500 to 600 mm, and after the first stage of the crushing it will be reduced to 150 mm to 200 mm, and then again it is sent to the second stage of the crushing wherein the size is further reduced to different sizes, right? And thereafter we are getting the coarse aggregate. As far as the fine aggregates are concerned, in this particular plant they have vertical shaft impact crusher which are used to produce good quality fine aggregates. uh, a similar process map can be seen in South Africa, Cape Town, South Africa, wherein the aggregates are crushed with the help of the jaw crusher. But however, the second crusher in this particular case was the gyratory gyratory crusher in order to get the good shape aggregates. So two things happens when the after the aggregates are being crushed. One thing, the big size aggregates. So normally more than 20 mm size aggregate, if it is not required, then it will again be sent for recrushing, right? And then also we have seen that a lot of dust will be generated because of the crushing process, right? And then there has been a lot of research which has shown that this dust that is formed or generated during the crushing process can be used as a filler material because of its high surface area. This dust is nothing but the cementitious system. That means the mortar that is attached to the natural aggregate, the mortar that is attached to the aggregates. So this dust is the mortar. So obviously it will be having lime bearing compounds. So obviously this can be used as a SCM if properly processed. In fact, the recent literature shows that this dust can even be used to replace cement or for the cement regeneration because of its properties, and also if it is processed well. So this dust is called as concrete fines, and then the particles which are less than 300 micrometer could be considered as concrete fines. Uh, the issue, there are some issues with the stationary recycling plant. For example, let's say this is my area and this is the recycling plant. So if the source is here or the source is here, and then trucks are used to transport the C&D waste generated at a location to the recycling plant. So a lot of number of truck trips will be required to transport the waste from the location to the crushing unit, right? And we know there will be a lot of CO2 emissions because of the utilization of the fuel in these trucks. So one of the way to reduce the carbon emissions because of the due to the movement of the C&D waste is by directly taking the crusher directly to the site, and this is called as on-site recycling. So the process that will be followed for the on-site recycling will be same as that done for the stationary plant. The only difference is that here the crusher will be coming to the site, right? So here you can see initially size reduction is done with the help of the jackhammer, and then thereafter the small sizes concrete chunks are directly fed into the crushers, and thereby getting the aggregates. And then also the latest machines are also having the sorting system, so we can get different sizes of the aggregates after crushing the C&D waste. So traditionally there were issues with the on-site recycling. For example, let's say if we have to do the recycling in the residential area, so because of the crushing, dust will be generated. So nowadays water is being sprinkled during the feeding system only, so as to reduce the emission of the dust. The other issue is the noise. So but nowadays advanced crushers are coming which are able to reduce the dust, reduce the noise to a considerable level. So now coming to the point, so initially we discussed that after 40 to 80 years we might not be having the good supply of the natural aggregates, so that's why we have to use the recycled concrete aggregates. But if you see globally, there are different codal provisions, and wherein although 100% replacement of the natural aggregate by the recycled concrete aggregate is allowed, but it is mostly for the non-structure elements, not for the concrete structural system. So when it has to be used for the plain concrete systems, then the replacement level is mostly is around 30%, and then if it is used for the reinforced concrete system, the percentage replacement reduces. So that means we cannot fully replace the natural aggregate with the help of the recycled concrete aggregates. So why is it so? There are different reasons, but one of the primary reasons is the added mortar. So what happens when we recycle the concrete chunks, it will have aggregates, and then around the aggregates will be having the cement mortar from the parent concrete. So this cement mortar paste is highly porous in nature, and then if you see the coefficient of water absorption of the recycled concrete aggregates because of the added mortar could be around 4 to 5 times than that of natural aggregate. Similarly, if we see the density of these recycled aggregates, because of the sticking of the added mortar, the bulk density of the recycled concrete aggregate also reduces. So if we use this recycled concrete aggregate in the new concrete system, so what will happen? Multiple ITZs will be formed. So what is this ITZ? It is interfacial transition zone. So let's see in a conventional concrete what happens. We have a natural aggregate, and then it's a mortar system around the aggregates. So there will be only one interfacial transition zone between the aggregate and between the mortar. But in case of the recycled concrete aggregate, because of the presence of the added mortar, multiple interfacial transition zones will be forming. So here in this picture you can see one transition will be obviously between the aggregate and the mortar, because the mortar will not be totally binding or covering the aggregates. There will be some patches from which the new mortar can go and then bond with the aggregate. The other interfacial transition will be between the old mortar and the old aggregate. And then the third interfacial transition zone could be between the new mortar and the old mortar. So obviously, when when this system is loaded, the crack can propagate from different interfacial transition zone or between different matrices. So for example, the crack can go through the new mortar, the crack can go through the interfacial transition zone between the new mortar and old mortar, the crack can go through the old mortar, or crack can go through the ITZ between the old aggregate and old mortar, and in fact the crack can go in case of the aggregate. But mostly for most of the structures, what we have seen, that the crack will be passing either through the old mortar or through the interfacial transition zone between the old mortar and old aggregate. So this shows that the quality of the concrete made with recycled concrete aggregate will mostly be dependent on the concentration of the added mortar and not to the new mortar. So that means if you keep on increasing the cement contents, the improvement in the strength might not be significant as compared to natural aggregates, right? So that means the added mortar content can be considered as a culprit. So this added mortar content depends upon numerous parameters. So let's see what are these parameters. The first thing is that the added mortar content decreases with the increase in the size of the aggregate. So obviously when we have small size aggregates, it has more surface area, and then obviously the added mortar content will also be higher. So as the added mortar content increases, we see the properties of the aggregates significantly reduces. For example, one of the important properties of the aggregate is coefficient of absorption. So as the added mortar content increases, the water absorption also increases. So thereby it will be having a significant effect on the concrete properties made with recycled concrete aggregates. The other parameter on which the added mortar content depends is the grade of the panel concrete. So let's say we are getting two recycled concrete aggregates, one from M90 grade concrete and one from M10 grade concrete. So the difference will be between these two recycled concrete aggregate is that the bonding between the aggregate and the mortar will be higher, significantly higher in the recycled concrete aggregate that we are receiving from M90 grade concrete, and then the bond strength between the mortar and the aggregate will be significantly lesser in case the recycled concrete aggregates are produced from lean concrete mixes. So obviously if we crush both these concrete chunks with the same crusher, so because of the lower bond between the mortar and the aggregate, the chances of removal of the added mortar will be higher, right? So this same thing can be seen in the graph, wherein the added mortar content is higher in case of the concrete, in case of the recycled concrete aggregate that are generated from high strength mixes, wherein the added mortar content is lesser in case of the concrete which is made with lesser highest water by cement ratio or lower strength. The other thing that will be affecting the added mortar concentration is the crushing stage. So if we are crushing, let's say this is the same concrete chunks, and if we are crushing it, recrushing it again and again will be able to remove the added mortar significantly, as shown by these figures, right? So in nutshell, what we have seen, as the added mortar content increases, the strength of the concrete made with recycled concrete aggregate will also be reducing. So that means we have to address this added mortar content. Okay, so there are different techniques available to address the properties of the recycled concrete aggregates, and these can be put in two buckets. One thing is surface modification, the other thing is the total removal of the added mortar. Okay, there are other techniques also, very simple techniques. For example, changing the mixing approach. So normally what happens, we place the coarse aggregate, fine aggregate, everything together, and then we'll feed the water, and then the concrete will be produced. But we can, since these recycled concrete aggregates are highly porous, and we know the total absorption by the recycled concrete aggregate will be taking some time. So what we can do, we can add partial water to the coarse aggregate initially. So coarse aggregate and fine aggregate can be fed, and then partial water that is required can be put along with the aggregate, so that the surface, if let's say this is the aggregate, the surface pores can be filled by this water, and then this aggregate will not be able to absorb the water from the mixing water for our concrete system, right? And this mixing approach is called as two-stage mixing approach. Nowadays, filling the surface pores of the recycled aggregate by the cementitious binder is also getting popularity. So here in this case, what happened, whatever the fine material we are having, for example, cement, silica fume, fly ash, whatever we have, we can add water along with these materials, and then we can put the recycled concrete aggregates, mix them well, so that what happens, these finer portions will be able to address the porosity of the recycled concrete aggregate, and that's how we can improve the properties of the concrete. The other best technique which shows promising results is that we can directly soak the water before use, but it will be difficult to soak the finer portions of the recycled concrete aggregates, right? So uh, slurry impregnation technique is also getting very much attention nowadays, because what happens, as we can see in this picture, the recycled concrete aggregates will be having a lot of pores and cracks and poor interfacial transition zone, right? Because of the added mortar. So all these things are there in the added mortar, right? So what we can do is that we can place this recycled concrete aggregates in a bucket, and this bucket will be having these slurries made with different mineral admixtures. So they could be different mineral admixtures ranging from fly ash, silica fume, granulated blast furnace like, or in fact this cement slurry can also be used. So when these aggregates are submerged in these slurries made with different mineral admixtures, SCMs or cement, for different concentrations, so what will happen, the pores are filled, these cracks are addressed. In fact, in some of the cases, the interfacial transition zone between the aggregate and the mortar has been seen to be enhanced. So how this mechanism works, by this mechanism, so there are basically three mechanisms by virtue of which the slurry impregnation techniques work. First thing is the filler effect. So let's say when we are using the some material which is highly finer, so obviously it will go inside the added mortar and then it will be able to fill these pores. So that is the filler effect. The second thing is the secondary hydration of the calcium hydroxide. As we know, this is a hydrated added mortar, so it will having calcium silicate hydrate, it will also be having calcium hydroxide. So when we are using certain supplementary cementitious admixtures as a slurry material, so obviously it will react with calcium hydroxide and it can lead to second formation of the calcium silicate hydrate, therefore reducing the pores and reducing the cracks, right? And the other thing is that hydration of the unhydrated cement particles. As we know, the complete hydration of the cement will be taking too much of time, and when the recycled concrete aggregates are being produced from some recently built structures, in that case there will be significant quantity of the unhydrated cement particles, and when we are keeping these aggregates into the slurries, so water will go inside and will be leading to the hydration of the unhydrated cement particles. But however, this technique depends upon numerous parameters. For example, which is the material that we are using. So literature shows that when microsilica is used, it will be able to reduce the pores by more than 50%. Similarly, it depends upon the concentration of the slurry, how much of the material we are adding, then it depends upon the total soaking duration and obviously the fineness of the slurry. The other technique that that can be seen in the literature is the self-healing of the added mortar. So there are various techniques of the self-healing. One of the technique is by using the bacteria. So normally what happens in this case, some urea will be mixed with the concrete, and then this urea will be releasing certain bacteria, and this bacteria will be responsible for the deposition of the calcium carbonate in the pores and the cracks. But however, there will be issues obviously, because some of the bacteria might not be able to survive in the alkaline environment, right? The second thing is that culturing of these bacteria will be difficult, and then the working of these bacteria depends mainly on the temperature and the humidity, and at the site it will be difficult to maintain that temperature and the humidity. However, the other self-healing technique is through the carbonation. So what we can do, we can use the aggregates, and we know in this added mortar content calcium hydroxide will be there. So the carbon dioxide can be feed into the system under pressure, and then it can react with calcium hydroxide and form calcium carbonate, leading to the improvement in the properties of the added mortar. But mostly these techniques might not be adopted into the field, right? But we have few incidents wherein the carbon dioxide is directly injected into the fresh concrete, and then the results show that injecting the CO2 in the fresh concrete will not compromise with the concrete performance. Now coming to the techniques wherein we are totally removing the added mortar, right? So the added mortar can be effectively removed, or not fully, partially, at the generation point only. Let's say in the recycling plants, if you are having multiple stages of the crushing, so obviously it will be able to reduce the added mortar effectively. And also the study that has been conducted at IIT Madras shows that by changing the crusher type also we can able to effectively reduce the added mortar. For example, in this case, the added mortar content for different sizes of the aggregate was found to be higher in case when the concrete chunks are crushed by jaw crushers, right? And in fact, when the crusher was changed to horizontal shaft template crusher, it so it reduced the added mortar effectively, right? The other important technique to remove the added mortar is to submerge the recycled concrete aggregate into the chemical solution. So various chemicals can be used for weakening the added mortar. For example, hydrochloric acid can be used, sulfuric acid can be used, and phosphoric acid can be used. And then so normally what happens, these acids will be mixed with the waters, and then the RCA will be submerged in that, so it will be leading to the weakening of the added mortar, and then by providing some scrubbing, the added mortar can be removed. However, there will be some issues. For example, if the concentration of the acid is more, it may affect the aggregate quality. Also, this technique might not be sustainable, right? And then obviously we need to consider the associated cost as well. So the best technique that can be seen in the available literature is thermomechanical beneficiation technique. As we discussed, the added mortar, the hydrate, it will be hydrated, so it will be containing calcium silicate hydrate, it will be having calcium hydroxide, and in certain cases it can have calcium carbonate. And we know that the dissolution of the calcium silicate hydrate will be happening at around 230 degrees centigrade. Similarly, between 400 to 500 centigrade, the calcium hydroxide will be dehydrated, and and then when the concrete is heated at a temperature of 700 to 900 degrees centigrade, calcium carbonate can also be dehydrated, right? So normally in this technique what happens, obviously the concentration of CHS and calcium hydroxide is significantly higher than the calcium carbonate, so the concrete chunks of size around 50 mm are kept in the oven and then heated at a temperature of 500 degrees centigrade for around 1 hour. So it leads to the dehydration of the hydrated compounds, right? And also different other mechanisms will also be happening, right? So for example, we have the coefficient of thermal expansion of the aggregate is different from the coefficient of thermal expansion of the mortar. So obviously because of this difference in the coefficient of expansion, the weakening of the added mortar will be done. And so after keeping this oven, these aggregates, these concrete chunks are kept into the open environment, or you can say at the ambient temperature. So there will be thermal shock, and because of the thermal shock, again the weakening of the added mortar will be happening. So because by virtue of these three mechanisms, the added mortar is already weakened, and now the only thing required will be to provide some scrubbing. So these concrete chunks can be kept in the milling machines, and then by virtue of the scrubbing, the added mortar can be removed. So here there is a comparative study that has been done wherein the thermomechanical beneficiation RCA is compared with without treatment RCA, and also with the industrial produced RCA. Here you can see the properties of the thermomechanically beneficiated RCA is significantly higher than the other aggregate. In fact, the density was even higher than the conventionally used granite aggregate that are found in India, right? So and the other important important benefit with respect to thermomechanical beneficiation technique is that it is not only improving the quality of the coarse aggregate. For example, here these are the coarse aggregate wherein we can see they are completely free from the added mortar, but this technique will also be producing high quality fine recycled concrete aggregate. For example, here in this figure you can see the density of the treated RCA is 2.35, which is significantly higher than the untreated version and the industry produced RCA, right? So but there will be some issues with technique because we are using electricity to heat the aggregates, right? So if we see from the sustainability point of view, this might not be sustainable. So one study was conducted at IIT Madras wherein the fuel was changed from electricity to solar energy, concentrated solar energy. So normally what happens at the solar plants, the solar energy is used to generate the electricity. So normally they have the parabolic disc which will be used to divert the sun rays directly to one receiver. So normally if you see, these receivers are hollow from inside. So the concrete chunks can be kept inside these hollow blocks, and then that sunlight can be directly fed over this receiver, and then it can be heated to a temperature of around 500 degrees centigrade, which we have used in thermomechanical beneficiation techniques. Sorry. So normally, these kind of plants will be having a lot of parabolic disc for generating the electricity, right? So obviously they will be having a lot of receivers. So that means the quantity of treated aggregates can be higher depending upon the number of the system that one factory will be having. So this is a line diagram which is showing what are the various parameters that was followed in this particular study. So in nutshell, what we can see, there are different beneficiation techniques from altering the mixing approach, wherein the water can be added into at different times, or the aggregates can be used in saturated surface dry condition. But the improvement in the concrete properties by following this surface modification techniques might not be significant. However, these techniques are very simple, and then no extra cost will be required, and these kind of the techniques can be applied directly into the field also. On the other hand, when we are following the removal of the added mortar with the help of the thermomechanical beneficiation techniques or the chemical techniques also, so in that case, the removal of the added mortar has been seen to be significant, and obviously the concrete that will be made with the treated recycled concrete aggregate will be much better. But we need to consider other aspects. For example, what will be the cost, whether these kind of techniques can be applied directly into the field, whether they are large scale applicable or not, right? And then what will be the corresponding energy consumption. These needs to be considered. On the other hand, if we are able to address the added mortar directly by using slurry impregnation technique or any other material, then these techniques might not able to improve the strength of the concrete made with RCA as significant to as compared to where we are using where we are totally removing the added mortar. But these techniques are considerably better than the other approaches, for example different mixing approach, and these techniques might be large scale applicable, and obviously again, because we are using different mineral admixtures, supplementary cementitious admixtures, so again we need to see the cost and the energy consumption. So yeah, thank you very much.